Okay, so now that we have reviewed what a function is and how to use function notation, we are going to meet some of our most important functions that we visit this year. And so we're going to start with a function that is probably very familiar from Algebra 1, and it's the linear function, the linear parent function. Any kind of parent function is the most boring version of that function family you could have. And so the linear parent function has a y-intercept of 0, 0, and a slope of 1, up 1 over 1. And so the equation for this guy is f of x equals x. And so whatever I put in for x, that's basically what I'm getting as the output as well. And so if I plug in 0 for x, I would get 0 for y. If I plug in 1 for x, I get 1 for y. If I plug in 2 for x, I would get 2 for y. If I were to plug in -1, I would get -1 as the output. -2 as the input would give me -2 as the output. That's why you're seeing these points on our graph. And so significant points are just the points you would need to recreate the graph. And so since we can plug in anything for x, domain is all real numbers. And then the range would also be all real numbers since we can get any output we want. Using our fancy R is another way we can say all real numbers. Our next parent function is the absolute value parent function, and the equation for absolute value is f of x equals the absolute value of x. And what absolute value does is it measures the distance of any number from 0. And so if I were to take the absolute value of 3, I would get 3, because 3 is 3 away from 0. -3 is also 3 away from 0. And so the absolute value of -3 would be +3. And so essentially when you put these absolute value bars around a number, you're basically saying take the positive version of it. And so if I were to plug in 0, the absolute value would be 0. Absolute value of 1 is 1. Absolute value of 2 is 2. If I were to plug in -1 to the function, I would get +1 as the output. Absolute value of -2 would give me +2. And so notice the first 3 points, very, very similar to the linear parent function. But on the left side of the graph, we only get positive output. So it's like the other part of the line is flipped up. And that's why we have that V shape for our function. And so the domain, just like the linear function, is all real numbers. It goes forever to the left, forever to the right. We can plug in any number we want. The range, however, would be 0 to infinity, since we can't have any numbers down here. So it starts at 0 and the function goes up from there. We could say all real numbers using our fancy R, and then the range we could say y is greater than or equal to 0. Notice the use of the bracket and the line underneath because we equal 0. The quadratic function is another function that's probably familiar from Algebra 1. The equation for the parent function is x squared. And so this time, when we plug in different numbers, we square all of our inputs. And so if I were to plug in 0, 0 squared is just 0. If I were to plug in 1, 1 squared is just 1. 2 squared is 4. And so on. If I were to plug in -1, -1 squared is +1. That's -1 times -1. Anytime you multiply two negatives, it's going to become positive. And so -2 squared, -2 times -2 is +4. And so here we have 0, 0, 1, 1, and then the point 2, 4. This is no longer linear. It's growing a lot quicker. There's not a constant slope this time. So that's why we're getting this U shape. And so the domain, just like our other two functions, is all real numbers. Our range, very similar to absolute value, is always positive. Anytime you square a number, it's going to be positive. And so again, 0 to infinity, or y is greater than or equal to 0. Notice we have the bracket and the line because this function does equal 0. We want to include 0 in the range. Our next function is probably very new. We did not talk about this in Algebra 1, but it's very similar to quadratic. It's cubic. So this time we are going to cube all the inputs. So we're going to plug in 0 to the function. We're going to plug in 1. And we're going to plug in 2. We're also going to plug in -1. We're also going to plug in -2. 0 cubed is just 0. 1 cubed is 1 times 1 times 1, 1. 2 times 2 times 2 would be 8. And then coming down here, -1 times -1 times -1 would get me back to -1. Because -1 times -1 is +1, times another copy of -1 would take us back to negative. Same situation happens with -2. -2 cubed would give me -8. And so looking at our graph, if we have the point 0, 0, 1, 1, and then 2, 8, it looks similar to quadratic, that U shape to the right, only now we can get the negative outputs again for the left side. And so that's why we have this change in concavity. It was concave up, and now it's concave down to the left. That's called a change in concavity or inflection point. It makes this S shape. And so our domain, again, just like all the others, is all real numbers. And our range is also all real numbers because now we have the negative outputs again. The rational parent function, also very new. The equation for the rational parent function, and rational just means fraction, is 1 over x. So this time our variable is in the bottom of a fraction. And so if I plug in 1, I would be getting 1 over 1, which is just 1. If I were to plug in 2, my output would be 1 over 2, which is 1/2. If I were to plug in 1/2 to this function, I would be getting, let me switch colors, 1 over 1/2. And so the way you divide by a fraction is you multiply by its reciprocal. You flip it and multiply. And so 1 times 2 over 1 is just 2. And so the output here would be 2. And so basically this rational function is flipping our input. And so if I were to plug in -1, I would get -1. Plugging in -2 would give me -1/2. And then plugging in -1/2 would give me -2. And so when we look at these points, we have the point 1, 1, 2, 1/2, and then the point 1/2 takes us back to 2. Similarly, we would have 3, 1/3, and then 1/3 would give us the 3. And so that's why we get this branch of the function right here. And when we plug in -1, we get this point -1, -1. Plugging in -2 gives us that -1/2. -1/2 gives us -2. And so that's why we have two branches of this function. It looks like two functions on the same graph, but it's actually one function split into two different branches. And the reason why that happens is we have to look at what happens when we plug in x equals 0. And so if I try to plug in x equals 0, I would get y equals 1 over 0. And then 1 over 0 is undefined. If you were to type 1 divided by 0 in your calculator, it would say error. You can't divide anything by 0. And so that's why at the x equals 0 line, this vertical line x equals 0, we have what's called a vertical asymptote. Okay, and that's because we're not allowed to plug in x equals 0. And so you're seeing there's no input or output to go with x equals 0. And so for our domain, we have every single number in the domain. This function goes forever to the left and forever to the right, but the only value we don't get is x equals 0. And so the way we say that is we can say all real numbers, comma, x cannot equal 0. The way we write this in interval notation is we can go from negative infinity to 0, parenthesis, union with 0 to infinity. We skip over the 0. We talked about how to exclude an element from the domain in our interval notation notes. So negative infinity to positive infinity, but we just skip 0. And using these parentheses instead of brackets shows we don't actually equal the 0. The same thing happens in the range. I'm going to switch colors to green. And so notice there are no points along this horizontal line right here. This horizontal line is the y equals 0 line. So at y equals 0, we have what's called a horizontal asymptote. And that's because there's no value that we can plug in for x to get y equals 0. If I plug in 100, or if I plug in 1,000, if I plug in 10,000, we can get really, really small, but we're never actually going to get to 0. And so you see that this function is approaching 0 from both sides, but never actually reaches it. And that's what an asymptote is. Anytime your function approaches a line, but never actually equals it or touches it, it's called an asymptote. And so in our range, we have all real numbers except y can't equal 0. And so the range would look very similar to the domain. Again, we have to skip over this horizontal asymptote. This is probably the most complicated function we have because we have two asymptotes. We have a horizontal asymptote and a vertical asymptote. So make sure you make note of that because this is the only function we have that has two asymptotes. This next function is going to be familiar from Algebra 1, the exponential function. We're going to look at several different exponential parent functions, but for now, this particular parent function is f of x equals 2 to the x power. And so this time, our variable, I'm going to highlight, is up in the exponent. And so as we plug in values for x, we have to plug it in for the exponent. And so we're going to plug in 0. We're going to plug in 1. We're going to plug in 2. And we're going to plug in 3. Okay, so 2 to the 0 power is 1. Anything raised to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. And so that's going to give us our y values 2, 4, 8. And so as we look at these points on the graph, there's our 0, 1. There's our 1, 2, 2, 4, and 3, 8. This function is growing very quickly because it's doubling as we go to the right. And as we go to the left, it's getting cut in half. So this would be 1/2, 1/4, 1/8, 1/16, and so on. And so this function, as we keep going to the left, is going to keep getting cut in half. And so we're going to get very, very, very small to where we're practically 0, but we're never actually going to get to 0. You can't plug in enough numbers to actually reach 0 by cutting in half. And so we have another horizontal asymptote for this function. Okay, and so I'm going to label this as a horizontal asymptote. Again, at the y equals 0 line. This is the y equals 0 line, this is the y equals 1 line, y equals 2 line. Any horizontal line has a y equals equation. That always throws kids off. Any vertical line, this would be x equals 0, this would be x equals negative, it looks like -2. This would be the x equals -5. Vertical lines have x equals equations. I don't want that in the notes. I just wanted to clarify that. And so we have a horizontal asymptote at y equals 0. And so for our range, it's going to be very similar to what we had on the last slide. All real numbers except, oh, actually, that is not true. If we look at this function, it never goes below 0. On the previous slide, it did have a branch below 0. So this function has a range that is just 0 to infinity. And we can include the bracket. No, I am messing this up. Since we never actually reach the 0, we're going to use a parenthesis and go from 0 to infinity. That's the difference here, is can't equal 0. And so in inequality notation, we are not going to have the line. Our range goes from 0 to infinity, not including the 0. We have to stay strictly above the horizontal asymptote. The range, or the domain, is again all real numbers because we can have any possible value for x. This function goes forever to the left and forever to the right. It looks like it gets cut off and has a vertical asymptote, but it does not. It is just a very steep function, but it does keep going to the right forever. The logarithmic function is, we're going to explore in detail later. For now, all you need to know is that the equation for this function has the word log in it. And so the equation would be log of x. And there's actually a button in the calculator you've probably seen for log functions. And what log functions are is they are the complete opposite of exponential functions. It takes the x and y points of an exponential function and completely flips them. And so the only significant point you need to know for the log function is that if you plug in 1 to a log, you'll always get 0. It's always going to have that x-intercept. The other important thing you need to know about log functions is just like this exponential function had a horizontal asymptote, The log function has a vertical asymptote. And so our domain this time, not a bracket, is 0 to infinity, or x is strictly greater than 0 because we only stay to the right of the vertical asymptote. And then our range, it goes forever down, and then even though it looks like it's not going to go up very high, it does go up just very slowly. So range would be all real numbers. Okay, so vertical asymptote, domain is to the right of the asymptote, so 0 to infinity, range all real numbers. Square root will be a little more familiar. We only have 2 more functions left. The equation for square root is square root of x. And so what the square root does is it unsquares things. So when we're picking values to plug in, we want to make sure we pick perfect squares so that we get nice, pretty outputs. So 1 would be a perfect square, 4 is a perfect square, 9 is a perfect square. And so the square root of 0 would be 0. If we unsquare 1, we would get 1. If we unsquare the 4, we would get 2. And then the square root of 9 is 3. Okay, and so we see the point 0, 0, 1, 1. Come over here, 4, 2. Come way over here, 4, 9. 9, 3. And so one thing about square roots is you are not allowed to take a square root of a negative number. If you tried to plug that into your calculator, you would get error. And so the reason why is because you can't square a number and get a negative output. And so that is why we have this blunt starting point here at 0, 0. We can't plug in any negative x values over here. And so our domain, now we get to use the bracket, goes from 0 to infinity. And because we can't plug in negative numbers in 2 for the function for the input, we're also not going to get any negative outputs. So notice there's no part of the function down here. And so the range is also 0 to infinity. We are using the bracket for both because in both cases we actually equal that 0, 0 point. So bracket. And so in inequality notation, we would want to make sure to put the line under the inequality sign. All right, last function is the cube root function. So just like square root unsquares things, the cube root function uncubes things. And so a cube root looks just like square root, only we put a tiny 3 in the index of the radical. We can have 4th roots, 5th roots, whatever you put in the index, that's whatever power you are undoing in this situation. Okay, and so when we pick our inputs to plug into the function, we're going to want to pick perfect cubes this time so that we have good output values. And so 1 is a perfect cube. Our next perfect cube would be 8. And then also remember, we can get negative numbers from cubes. And so the cube root of 0 is 0, cube root of 1 is 1, cube root of 8 is 2, cube root of negative 1 is negative 1, cube root of negative 8 is negative 2. And so this looks like square root as we go to the right with that growth that way. But now we have the other half of the graph because we're allowed to put negative numbers into a cube root. It looks weird, but if you put this in your calculator, you would actually get an answer, negative 2, because negative 2 cubed would have given you the negative 8. And so our domain is all real numbers, and so is our range, because we have this S shape that goes forever to the right, forever to the left, and then it continues going up, and it continues going down, and so all real numbers in both situations.